Are you guys ready? You guys don't look ready. Arthur, Yvonne, you guys don't look ready. We're streaming? Okay, hello. Hi, everyone. I'm Abdallah. Nice to meet you. Are we going to close the door or going to keep it open? Oh, okay. Maybe keep it closed in a few minutes. Oh, okay, sure. So this is going to be a workshop on basically Neuropawn Hardware. So a little bit about me. I'm the founder of Neuropawn. I'm Calgary-based, and I create affordable neurotechnology so that students like you can gain the skills to join the workforce. That's really one of the things that motivates me is sort of like giving back to you guys, and that's really what drives me to sort of make affordable neurotechnology. So this is what we're going to go through, just my journey, what I've accomplished with Neuropawn, some neuroscience basics, basically how EEGs work, and then some BCI paradigms, and then a project walkthrough at the end. Not really a walkthrough, more like a introduction. So for my journey, so I graduated from the U of A. There's my degree. I think it's pretty useless. I don't think it defines me. I didn't learn anything in neuroscience that I'm sort of using right now in my daily life, other than maybe just like where the specific parts of the brain are. Most of my work involves basically like software development and electronics engineering. And then I ended up pivoting sort of out of neuroscience and sort of like into sort of like med tech at the end of my fourth year. I did a machine learning thesis with Dr. Ian Winship, and we basically did, or I looked at doing like medical image analysis. I thought it was really interesting. I thought it was fun. I thought I was making an impact. Um, but yeah, that's how I started basically into how I got into med tech. I was always into it, by the way. Even before this, like in high school, there was like this one project by Microsoft. It's called Project Emma. I don't know if you guys have ever heard of it. Have you? No? Okay. So basically what it was this woman had like a tremor that was drug resistant. And so Microsoft, like they have like a special development team. They went and made her a watch that counteracted her tremor. And I was like, this is the coolest thing ever. My grandma at the time had a stroke and she also got like a drug resistant tremor. So I was like, oh my God, this is like a perfect thing. Like I can try and help her, right? So that's what got me into sort of neuroscience at the very beginning and sort of like that neurotechnology. Um, the problem was during my degree, I wish we had more of that like hands-on neurotechnology experience. I never really got a good grasp on like what EEGs were, how they work. I guess that's sort of more like biomedical techno or biomedical engineering. But still, I think it's very pertinent to like what's going on nowadays, especially with neuroscience, as like obviously the biggest thing right now is machine learning and like melding neuroscience and just it's called like what is it called? Computational neuroscience. Melding those two things is like one of the biggest things in the neuroscience field. So I don't know why they don't teach this in school. They should, because it gives you a lot of critical reasoning, problem solving skills, and it helps you a lot with getting jobs after school. That's basically it. Um, yeah. So I guess to just go on and maybe expand on the hands-on learning a little bit more. Um, I did a presentation at U of C a couple months ago when they first started the block week for the first and second year engineering students. And I guess my biggest takeaway from university was university doesn't teach you enough. University sort of like I feel like students have been like sold this, I guess, like idea. It's not a lie, but it's an idea that you go into school, you get good grades, you do projects, and then you sort of get a job afterwards. And it can't be farther from the truth nowadays. I know all of you guys in the front row, all of your computer science, it is cutthroat in computer science. It is like literally everyone on top of everyone, and you're trying to beat like your peers in terms of like your skills, and you're competing with them for the same jobs. So how do you get ahead? How do you sort of, differentiate yourselves? You can't do that just through school. And so I think that's what university didn't teach me, and that's sort of why I was really ticked off, and I didn't end up going to my graduation because of it. I was like, this is stupid. Like, why am I going to this? I didn't really accomplish anything. I didn't learn anything. So yeah, I really, really stress this. If there's one thing you guys want to take away from this workshop, like leave all the neurotechnology out of it. This is just a very genuine advice. You guys should really focus on applying yourselves and differentiating yourselves as learners, as students. And yeah, and that's how you're going to get hired or do basically what you want in life. Okay, so I didn't get hands-on learning, but I sort of had this introspection. I was like, I wanted to improve my resume so that I could go and apply to jobs. Okay, now at the time, I applied to over 80 or 100 jobs, and I got a couple interviews, and I wasn't successful, unfortunately. So I looked back, I was like, you know what, my resume is lacking a little bit. There's only like a couple projects here. It's sort of lackluster. There's really nothing like special about me. Like I know that I'm a sort of like I'm very passionate about stuff, but I felt like my resume wasn't reflecting that. So I was like, okay, let me go and make a project that basically combined two of my passions. One was chess and the other was neurotechnology. So I wanted to create a brain-computer interface to play chess just by thinking about the moves. So I would use an EEG, take the signals, use those signals from the EEG, and then sort of find a way to interpret those signals and turn them into chess moves. However, when I went online to buy this headset, or this EEG headset, it was exorbitantly expensive. It was like north of 3,000 USD, right? And obviously, I didn't have a job. I just came out of school. I was still paying off my student loans. So I was like, how am I going to do this? How am I going to sort of like do this project? So it sort of shifted from how do I do this project to now how do I actually make an EEG? Because I thought, if I can't buy one, I got to be able to make one, right? There's got to be an alternative. So I was sort of resilient in that front, and after a bunch of research hours and early prototypes and looking at different papers, learning the fundamentals of electronics engineering, of like prototyping, PCB design, I basically figured out how to make an EEG, right? Or sort of this amplifier, this biosignal amplifier. And I'll explain what these things do in a second and all of their components, but this biosignal amplifier, I worked on it, I think, for over like 300 or 400 hours. And I came up with this puny little, 1 amp breadboard. Or I guess this is like 9 amps. And so I made this and I turned it on and I connected it to my Arduino. I'm like, oh, okay, this is a low cost option. This is amazing. I just salvaged some components that I had laying around, and it didn't work, unfortunately. So anyways, I kept iterating on the design. I didn't give up. That's one of the biggest things as well. Do not give up. I recently just ran into, like yesterday actually, ran into a mishap with manufacturing the headsets. And this has sort of happened throughout the Neuropawn's inception. I've had like hurdle over hurdle over hurdle, whether it's with software not working, whether it's hardware giving crappy data, or whether it's like dealing with customers or like basically people around you who are not supportive or whatnot. So there's always these hurdles, and you sort of always have to look long term and sort of envision where you want the company to be or where you want yourself to be in X years, or what's going to happen, what the outcome of what you're going to do is. So anyways, I kept iterating on the design until I finally came up with the prototype V1. I don't know if you can read it here, but it says V1. Anyways, This was a sort of like developmental board that I made, and it was based off of this chip. And then it worked finally after like 3 or 4 attempts. Um, and it was amazing because I tried recreating this. I'll tell you a story. I had the worst equipment ever. Okay, I had like a soldering iron that was 20 bucks from Amazon, and I don't know how I made that board. The pitch or the distance between these pins are like 0.2 millimeters. So I don't know how I didn't bridge any connections, and I got it on the first try. If that isn't a sign from God, I don't know what is. Because I made that board I think another 5 times, and every single time it did not work. So anyways, I was really, really thrilled that it did. And so then it worked, but it produced results or data that was super, super noisy. And so then I kept iterating on design as usual, added more filtering, added more stages, and this is eventually what I got to here. This is V3. And this included more, analog filtering, and it also allowed me to port to my Arduino really, really easily. So I thought to myself, I'm making all this stuff, and I'm spending a lot of time on this. There's got to be other students in the same position that I'm in who are sort of struggling to find work, want to improve their like resume or just want to do a project, but they can't because stuff is so expensive. So that's where basically the inception of Neuropawn came, and that's why I just kept pushing with this idea. So this culminated to these two, I guess, products that we have. We have more products, but they're not listed here. So this is our Neuropawn headset, EEG headset. It's based on the 1010/1020 EEG node placements. I'll get into a little bit more detail about it later. And this is our Neuropawn Nightboard. So as you guys can see, we have sort of like a chess theme, or I have a sort of chess theme for Neuropawn. And it's because there's 2 reasons. The initial was because I wanted to create a chess brain-computer interface, but also I want Neuropawn to be that first step for young students like you guys, first years, or maybe the people who want to get into neurotechnology who haven't yet, right? So I want to be that first step for you. I want to sort of hold your hand and make sure that you understand what you're doing, get some projects in, get some experience so that you can sort of build your way up to buying a more expensive headset or whatever. Okay, so Neuropawn's achievements. Our hardware, that's the biggest thing. Obviously I don't have an electronics engineering background. I don't have a software development, a software engineering or computer engineering background, and I was able to make all of this like single-handedly by myself. And it's not me trying to brag, but it's I want to sort of give it to you guys as like inspiration. Like you guys can do anything that you put your mind to, right? Not in a million years would I have thought I'd be doing this. And so if you guys want to become an astronaut, if you guys want to become, I don't know, a giraffe, put your mind to it. You can do it. Yeah, jokes aside, this is one of our achievements. It's the hardware. We tried to make it as sort of like user-friendly as possible, and we'll do a little demo of this afterwards. That's basically what the project is going to be about. That's it. We have a Bluetooth board as well, which I haven't showed, but that one's still in development right now, and this is something we're working towards. Alrighty, the second achievement, I would say the biggest achievement, was being a finalist for the Neurotech pitch competition. This was during Adventures 2024. This was in May, and we basically, I applied to this pitch competition. I submitted an application for Neuropawn, and we got accepted as like a finalist. And we were competing with like 4 other established companies for $25,000. And I was like, this is crazy. And here's us. We're just like some kids, basically. We're like we looked like kids in, I don't know, like the White House. Like these are people who are like seasoned veterans, doctorates, PhDs, you name it. These guys have it, and we were just sort of these like kids with that are being like foolish or whatever. Um, so I think this is sort of like good foreshadowing because I feel like, the young people have like fresh ideas and fresh minds, and they sort of try and break the status quo, which is really why Nat was such a big support for us and why we aligned so closely. Yeah, so during this time, by the way, this is when Kevin, right here, and Stanley, right here, you can't really see his face, but he's backwards. They joined the company, and Kevin is he is, what is Kevin? Kevin is he is one of the most intelligent people I know. Let's just put it like that. He has worked at Apple, Huawei, Musashi, Traject. He has like a ton of experience under his belt, and he's really, really forward thinking. That's what I love about him. And then Stanley. Stanley is one of the best people's person I've ever met ever. He is in mechanical engineering at the UFC, and he's sort of like our business guy. He deals with all of like the networking and whatnot, and I'm really grateful for his input and for his contrasting, I guess, like viewpoints. It's good because he sort of thinks more like how does this person think, whereas like me and Kevin will sort of think, okay, like how would like an engineer think about this or something. And so like he's a really good like contrast. You always need that sort of dynamic, even in teams. Try not to get into a sort of like group think situation where you're just like all echoing the same viewpoint. Try and speak out, look for flaws in whatever you guys are working on. I'm saying this to you guys, but it's also to you in the back. You guys should be like if there's flaws in whatever you're doing, you should point it out always and try and fix it. Try and think outside the box. Alrighty. So then this is I guess like one of our also pretty big achievements. So there's me, and then this is my team, my capstone team at UFC. The better school? No, I'm joking. So this is the UFC 501, 502 capstone. These guys are super talented. They're fourth year biomedical engineering students. Some of them are in software, some of them are in mechanical, and they're basically working on making electrodes, active electrodes that fit a variety of hair types. We'll get into basically what active electrodes are, what passive electrodes are, and yeah, we had some experience. The natHACKS team and we were basically just looking at the Neuropawn Hardware today, and obviously my hair is pretty short, but the electrodes that we have don't work really, really well. And this is a problem with basically all headsets. The electrodes are sort of like, there's a running joke that electrodes are made for like bald white men. So yeah, they don't really work that well for people with long hair. And that's what we're trying to fix. So we have a very diverse group, bunch of different hair types, and we're trying to make it happen. Alrighty. All right. Neuroscience fundamentals. How many of you guys know about neuroscience? Hands? Feet? No? Alrighty. Okay. How many of you guys have heard of the action potential? What is the action potential? Jesu.
It's like the potential to change or
So yes, an action potential is basically just how a neuron fires. Yeah, so that's correct. So this is how it happens. Here's the, like, I forgot what it's called. I should know this, I'm in neuroscience. But inside the axon, negatively charged, right? The proteins, negatively charged, outside positively charged, and it basically flips. And so then you have this sort of like depolarization wave that travels along the neuron, or the axon technically. And yeah, this is how axons work. They're sort of like this Resting membrane potential. I'm gonna go over this. Sorry, guys. You have a resting membrane potential, and they have this sort of like threshold. Certain receptors, like for let's just look at like I don't know, heat, right? So like you touch a hot stove, your hand gets hurt, and then you take your hand off. How does that work? What happens initially is your sensory neurons on your hand are at a resting membrane potential. When you touch something hot, those thermoreceptors, their protein structure changes. And so what that does is it opens these gates to ions, and it allows ions to enter the neuron, or the receptor technically, or the sensory receptor. So then what ends up happening is when the ions enter, the membrane potential, the voltage, changes. And it reaches this threshold voltage. And then when it gets to this threshold, there's something called the all or none response. You guys remember this? No? Bio 30? No? So basically what happens is like if you reach negative 55, you'll always go to the max. You'll always go to you'll always have a depolarization happen. So then after you depolarize, you go to plus 40, then you go back down, you go to this refractory period. It's called hyperpolarization. And then you go up to like your resting state. So why is this refractory period important? Does anyone remember from Bio 30? Yvonne, looks like you know. Serena? No? Okay. This is going this way. Why doesn't it just stop and go that way? Let's get some thinking here. Let's problem solve, guys. Come on. Alex, why doesn't it go backwards?
There's a difference in potential between the two sides of it. It can't fire positively charged on right. Can't fire again during the hyperpolarization.
Yes. So if I'm down here, my membrane potential is not negative 70 anymore. It's like negative 110. So then it's gonna take more stimulus to get me back up to that threshold. So that's why it doesn't go backwards. Important, very important. Very, very important. Okay, that's it about the action potential. That's basically it. Important thing to remember, wave. Wave. Okay. Alrighty. So, oh, no. Wave interference. Now we're going on to physics. Oh my God, physics and neuroscience. Who thought? Right? So, what is wave interference? Matvey. Actually, no. I forgot your name. Sean. What is wave interference?
It's when, I'm guessing when sound waves interact with each other and cancel.
Okay. What is that called? Just with a D. Which one of these is the one where they're canceling out?
Right.
This one. Why?
The top graph shows it's loud.
Okay, sure. But why specifically?
The top is canceling with the bottom.
Okay, exactly. If we look at one time point here, this negative, let's just call this negative, I don't know, like 20, positive 20 is canceling out. Done. So this is known as destructive interference. And on the contrary, the other is called constructive interference. So I don't know, do I have this? I didn't write a thing here. Anyways, the most important thing to know about this is we can basically have waves when they collide, they can either add together or they can either cancel out or make the amplitude bigger. Understood? Great. So why is this important? Well, this is really important because now we're going to talk about neurons and EEGs. Okay? So what ends up happening in your brain is EEGs are sort of just measuring, or the electrodes are measuring the electrodermal activity. they're measuring what's happening at the surface of your scalp. Okay? And what's happening at the surface of your scalp isn't due to just one single neuron. It's a collection, it's a consortium of neurons that are firing together, and all of their signals are being summated, and it's producing this sort of wave. Do you guys see that? Wave. Nice. So that's basically it. So when we're measuring at one specific node location, let's say this one F4, when we're measuring here, it's measuring everything underneath. It's not super spatially accurate. But yeah, it's basically taking what's happening, the collection of what's happening underneath. Yes. So what is F4? What is this? Weird number. Crazy. So do you guys remember the different parts of your brain, the different lobes? Do we know them? No?
Left and right.
No, that's hemisphere. Different lobes of the brain. Let's hear them. Okay, there's one. Come on, you're NeurAlbertaTech guys. You know this. Frontal, 1. Temporal, 2. Parietal. Occipital, nice. So the 1020 EEG system, my head is different than May's head. My head is different than Jesu's head, right? I have this weird, like, what is it called? The headset bump? Like my head is shaped weird, right? Like God made me this way, whatever. So we need a way to basically standardize how we are measuring or locating specific areas in the brain, called neuronavigation, right? What they would do if they had if we had unlimited money, each of you would get an an MRI to locate specific areas of the brain. We don't do that because that's very expensive, right? Not everyone can get an MRI either. So what we do instead is we use something called the 1020 EEG placement. And so what we do is we start here at the nasion, which is the deepest part of your nasal ridge, and we measure from this point through to the back of the head to the inion. And so it's not really that well labeled here, but the inion is sort of this, like, if you want to feel for it right now, the inion is like this protuberance at the back of your head. It's shaped like a little cross. It's kind of hard to feel. I fell on my head when I was on the back of my head when I was a kid, so it's kind of hard for me to feel because I have scar tissue there, but you can still feel it. It feels like a cross. So anyways, these are two landmarks that we use to measure someone's head, right? Because my head, different than Serena's. But what isn't different is the percentages. So our head shapes are similar, right? But the measurements might be a little bit off. My head circumference might be 56, Serena's might be 55 or something like that, right? So that would change the location of where her occipital lobe is by like a millimeter or like something along that nature. So anyways, we go up 10%, so that's why it's called 10%, and then we go 20% intervals, and we like basically mark each node location. So O stands for occipital, pretty standard, vision, occipital. P, parietal, so this is like sort of like your association cortex, like everything involved in like your senses and sort of like integrating your sensation happens here. Some vision stuff as well. Temporal, hearing, a little bit of like memories, a lot of memory stuff, but and then we have our frontal lobe vertex. This is sort of like, this is where you would actually mark this here. The C stands for center. And C3 and C4 is actually where you would stimulate someone's head, and that is responsible for moving their hands. It's crazy. If you guys ever heard of TMS? I think you guys have. I told you about it. TMS, May? What's TMS? Yes. So you get a big magnet and you put it over someone's head and you turn it on, and it causes their neurons in that specific area to activate. The craziest thing ever. It's like insane. And so anyways, you put it over this C3 spot and you turn it on, and then the person's hand starts twitching. It's crazy. Anyways, this is really important because all EEGs are sort of mapped in this way. This is how we standardize my head to Serena's, to Matt Vase, to Alex's, to Jessu's, to Arthur's, to Yvonne's, to Sean, May's. I forgot your name. I'm trying to remember your name. Right? No. Rush?
Yes.
Yash.
Yashar.
Yashar. Oh my God. What a doozy. Okay. Anyways, important. 1020 EEG placement. This is sort of the neuroscience. That's why I didn't put it in like how EEGs work. But now I guess we'll move on to what are EEGs and how do they work. So EEGs are sort of like a big amplifier. And the best analogy I like to use is EEGs are like this. You're in a big concert hall at the Rogers Stadium. Is it called the Rogers Stadium? It's called the Saddle Dome, guys. Come on, Saddle Dome. The Saddle Dome in Calgary. Let's say Taylor Swift is playing. Okay? Obviously, Taylor Swift fans are very crazy. So everyone's screaming. And what you're trying to do basically is you're in the bowl 3, you're at the very top. You can barely see Taylor Swift, and you're trying to basically record your friend all the way at the other end of the stadium. You're trying to record them speak. That is essentially what an EEG is doing. It's picking up the whispers in your head. The reason I say it's a whisper is because your body doesn't produce that much voltage, doesn't produce that much power. So you can't really drive these electrodes that strongly. And so an EEG has a really complex job of removing all this noise and only taking in that sort of good signal. Make sense? Questions? Concerns? No? You sure? Okay, so one big component of EEGs is differential amplifiers. Okay, so differential amplifiers. Can someone tell me what differential amplifiers do based off of the slide? Sean? Look at the slide. What is it doing? No? Can't put it together? So basically what's happening is differential amplifiers take the difference between the non-inverting input and the inverting input. You can't really see it that well. Oh wait, no, did you guys add it? You guys didn't add the plus or minus here. Anyways, there's supposed to be a minus right here. So 3.3 minus 0.5 volts equals 2.8. So this is what you'll get on the output. This is on the non-inverting. This is on the inverting. And this is what you'll get on the output. Okay? Really crucial. This is basically how all EEGs work right now. Just for right now. In the future, maybe we'll have different technology. So, why is this important? Well, most EEGs, or at least the ones that you're going to use today in this hackathon, are sort of all referenced to these 2 points, A1 and A2, right here, these little earlobes, right? Why would we choose to reference these earlobes? Matvey, you know the answer to this.
The kind of ambient.
Answer using this. Why would we want to use the earlobes?
It subtracts the residual noise away from the signal you're actually trying to find.
Close. So my earlobe would go onto the inverting input. Okay, so what's happening here? 3.3 minus, what's the voltage at your earlobe? What's happening at the earlobe? Exactly, nothing. It's basically isolated from your body, right? So they use either bony parts. I know some people use their elbow, some people use their ankle, basically bony parts of their bodies, or they use their earlobes because they're isolated. So they put them at the non-inverting input, sorry, at the inverting input, so that they can get sort of like a true reading at, let's say, FP1 or F3 or FZ. One more thing I didn't mention about the 1020 system is everything on the left side is odd. Everything on the right is even. So you see 2, 4, 6, 4, 4, 4, 8. Anyways, that's also a good way to differentiate. So anyways, that's really, really important because every single EEG you guys are going to use has this like functionality where you're basically taking the reference to a specific point that is determined to be 0. Questions? Nope. Okay. Now, how do I listen to my friend who's at the end of the Saddle Dome and there's a bunch of Taylor Swift fans yelling? What do I do? I need to do what, Sarita?
Actually, kind of speak of the noise being higher and noise that here, so I
Yes, specifically. So there's different types of filtering, right? That's why it says like Q0.1, Q1, Q10. It's basically just how strong the filter is. And so there's a bunch of different in electronics engineering, and I learned this when I was doing my research. There's a bunch of different topologies or ways that you can like set up your circuit to make filters. And they all have different graphs and they all serve different functions and they all have different complexities, costs, blah, 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 and whatnot. It's really not that important. The most important thing is you want to basically remove noise from the signal. So, Yashar, what's the biggest contributor of noise in this room right now where I'm standing? It's not my voice. No, I'm joking. So sound is a type of noise, but sort of think a little bit more abstract. Noise would be like, okay, Matt Bay, sure.
60 hertz.
Yes. Why is 60 hertz? How'd you come up with this weird number?
And that's probably something to do with those outlets behind you.
Yes, specifically. So you guys remember in physics, again, physics, I hate it, right? You guys hate physics. No, physics is fun. You guys remember parallel plate capacitors? Yes. Sean, you know what they are. What are parallel plate capacitors? Okay, let's hear it. Parallel. Yes, exactly. Okay, and then what's so special about parallel plate capacitors? Sort of. They basically build up charge, right? Okay, so imagine I'm this big ball of electrolytes, ions. I have all these different like charged molecules inside of me. Okay, and now these lights, basically everything above me is oscillating at 50, 60 hertz AC voltage. Like I'm basically a big capacitor. That's essentially what's happening. And what it's doing is it's horrible because it's influencing your signal. So you'll see like the difference between good signal versus bad signal can be the difference of just turning on or off the lights. Or just isolating yourself from power lines. That is one of the biggest contributors of noise. So you'll see in a lot of EEGs that you guys have, they'll contain analog filters for 50 and 60 hertz. They're called notch filters because they sort of take a notch out of the transfer function. Transfer just means like what is going through the amplifier or the circuit board. Okay, let's get some more. Let's get some more ideas. What's another source of noise?
Wait, 4 gigahertz?
Yes, that is another source of noise. So just like electromagnetic radiation. Why is that bad?
It would affect the signals going through the wires to the
Okay,
amplifier.
so it would induce a current or basically cause neurons to slow down, speed up, blah, 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 whatever. It's basically ruining what's happening through these wires. Do we have can I see the model? Actually, it's fine. We'll do it after. So you're basically ruining what's going through the wires with all this EMR. Like, let's say you're right beside, you guys ever heard of like tinfoil hats and stuff? Right? So why do they use tinfoil hats? What's like the reason? Block out the radiation, right? So they're blocking out the radiation because the radiation sort of like interfering with what's happening in their brain or whatnot. I don't know. Some crazy people think that. But it does happen in your wires. So you're not crazy for thinking that. Okay, so now this is a different type of noise. So you might see this on other like EEG systems referred to as bias, driven ground, active shielding, or I like to call it the right leg drive because that's initially what it was. So what is the right leg drive? The right leg drive it's a circuit that tries to remove noise that is common to both the inverting and non-inverting terminal of the differential amplifier. Is everyone clear on what a right leg drive amplifier or circuit is? We're trying to remove the noise that's common to this electrode, inverting, and this electrode, non-inverting. We're trying to remove that noise. We don't want to amplify the whisper, or we don't want to amplify the Taylor Swift Swifties, is that what they're called? Swifties? We don't want to amplify the Swifties screaming. All we want to do is amplify our friend at the very end of the Saddle Dome whispering. We don't want to amplify the Swifties screaming, or we don't want to amplify, God forbid, Taylor Swift, right? She's already loud enough, right? So anyways, the way that this works is Sean, you're an expert. This is so it's destructive. Destructive interference. What happens is you basically extract the signal, that common signal, to both of the electrodes, and you invert it. So you take this, you first amplify it, and then you invert it. Okay, you see how this is inverting? You invert it, and then you drive it back into the body. Why would you want to drive an inverted noise signal back into the body? Sean? One's here, one's here.
Cancel out the noise in the body.
Yes, it cancels out the noise. So what's happening is you're canceling out the noise that's common to both inputs. This is crucial, crucial. One of the deciding factors of like how you make a medical device or how you sort of, choose an EEG, you want to look for something called the common mode rejection ratio, CMMR. Common mode, no, CMRR. Common mode rejection ratio. So this basically just tells you if there is two common like mode signals, what is the drop off or how fast do they get thrown away from the signal? That's it. You want a higher number. Higher number is better. It means like less of the noise is going through the system. There's noise here. Less of it is coming out here. That's what we want. We want there to be a clean signal. So the Neuropawn Nightboard has this, by the way, and crucial. This is like a make or break. If you don't have this in your EEG or medical device, ECG, it basically ruins your signal. It's almost impossible to get a signal that is like robust without having one of these. Okay, so I've explained the right leg drive. I've explained how, EEGs worked. I've explained neuroscience background. And what time is it now? Oh my God. 5:15? 5:51. Oh, so we're on time. That's good. Alrighty. So now I'm going to talk about basically the different BCI paradigms. This is sort of the meat and potatoes of like what you guys are doing at natHACKS. So what are BCI paradigms? BCI stands for brain computer interface. It's how I can use my noggin to control the lights, to control Minecraft, to control chess. I'm basically using my brain, thinking about specific stuff, directing my attention to specific stuff without the input of my hands or legs, and I am causing action. That is in essence what a brain-computer interface is. And there's a couple of different techniques, sort of ways you can think about stuff to like cause other stuff to happen. It's called paradigms. So the first is called motor imagery. There's a bunch, but this is just the ones that I've decided to talk about because I think they're the coolest. This is motor imagery, and this is like magic. If you guys ever get the chance to do this, this is like sort of the craziest thing ever, and it's mind-boggling. The way that it works is if you think right now, everyone, let's take a little thought break. Think about moving your right hand and think about making and clenching your fist in this right hand. You guys thinking about it? Okay, so all of you that did that had the left part of your motor cortex activate, like this person. So you see here, motor imagery, they're thinking about clenching or moving their right hand. And what's happening? The left part of their, is this a heat map? Yes, the left part of their brain is activating. It's inversed. I don't know why they have this in the other way. This might not show what I want it to show. Anyways, the point is basically when you think about moving your appendages, your hands, your legs, you think about making a fist, you think about running, all of these get played out in your head. Your thalamus, which is your relay station in the brain, cuts off this signal. So it stops it from actually going. Yeah. You don't even realize, like, it's actually insane how specialized our like hand movements, our fine motor movements are. If you guys have heard of Neuralink, right? Obviously, right? Everyone? Have you guys heard the Neuralink guy, the guy who had the implant in his head, talk about how he's sort of like doesn't even, like, he can't even like comprehend that he's thinking that fast about stuff, and it's just appearing before he even thinks about it? That's how your movement works. You move before you even think about moving. It's the craziest thing. And your thalamus, which is sort of like the central relay station, stops or is like the executive is like, nope, signal you can't get past. Very important, because God forbid if I sort of become paraplegic, quadriplegic tomorrow, if I have like a spinal cord injury and I need to move a wheelchair, how am I going to do that if I can't use my hands or my feet, right? I'm not going to be independent. This is one of the biggest challenges for people who are paralyzed. So one of the ways that they can sort of circumvent this is they can wear these EEG caps, and they can think about moving their right hand, and it causes their wheelchair to move right. They can think about moving their left hand, it causes it to move left or whatnot. And so, yeah, anyways. Alrighty, that's motor imagery. Cool. Very complex though. Very, very complex. Really, really hard to get signals that are robust. From this, you will probably, if you were to do this for your hackathon project, you would need extensive signal processing. And most likely you will need to use machine learning. All right. Oh, one more thing about this. Because all of our brains are different, you will need to fine tune for every single person. So the neurons in my head right here might not fire as hard as the neurons in that specific location as Alex's. So his might fire a little bit stronger or a little bit weaker, whatever, right? The point is that it's different for everyone, so you need to fine tune for this. That's why you need machine learning. Yes?
So this makes sense for if you just think about moving your right hand and think about moving your left hand. But when you think it's like, say, moving your hand up or moving your hand down, how's it different? How would you see a difference
Oh,
in the signals?
so there's a, so, okay. So say one more time.
So what is the difference in the signals when you
Between like
think about
clenching your
a
fist?
different movement, say moving
Because you have, so there's something called the cortical, I should have probably showed this. It's called the cortical homunculus, right? The cortical homunculus is what? It's basically our brain is mapped from the top. This controls sort of like your feet, your genitalia, and like basically you move up and down, right? Starting at the middle of the brain controls feet, legs. A little bit more to the right, genitalia, upwards, stomach, keep going up. Then you have this huge representation for your hands. Your hands on the cortical homunculus look like, what do they look like? Like big, what's that guy? The guy who climbed up the beanstalk, what's his name? The really, I don't know, I haven't slept. So the gigantic dude, basically. Your hands are huge, right? And so the reason your hands are represented as this really, really large object is because your hands have a lot of sensory neurons, a lot more than your back. Have you guys ever done the experiment? Actually, let's do this right now because this might be interesting. So with a partner, if you guys are comfortable, just put like a couple of fingers on their back and have them guess how many fingers they have on their back. How many fingers does he have on your back? Okay, how many does he have? He had 4 fingers on your back. So you can't sort of sense, what's happening at the back, on your back, because it's not that important to you physiologically, right? Whereas like your hands, this is how you interact with the world. You need a lot of neurons here, a lot of sensory neurons in order to like visualize, like I can look into my backpack, touch stuff and grab my pencil case without even, looking. That's because I have a lot of sensory receptors and allows me to navigate through my backpack. It's called proprioception. Anyways, it's really, really important. So, okay. Yeah. So then you were talking about cortical, we were talking about,
Except for how you know it's your arms, but how do you differentiate different movements of your arms if it's the same area?
yes. So it's slightly different. There's different neurons for different, like movements.
So the heat map would be slightly off.
Yes. Yes, specifically. Alrighty. Now, this is called the P300 or the oddball paradigm. So this one is pretty interesting. You can't really do a lot with it other than make a cool game. Or maybe like do some neurofeedback stuff. What is this, like a 45-minute timer?
6 p.m.
Oh, it's 6 p.m. Okay. We'll move on. We only have a couple slides left. Yeah, we only have a couple slides left. Okay. So the P300 oddball paradigm. So this is basically like, okay, Matvey, you're looking for a black water bottle that is scuffed. Okay? So you're looking for this. Okay? You got it? I'm showing you this now. Okay? So what happens is your neurons don't fire. Then I go, okay, look at this. Look at this remote. Okay, still nothing happens. But then I go, here. Oh my God, you found the water bottle. That's the one you were looking for. So what ends up happening is as soon as you see this oddball that you're primed to look for, you'll have an elevated response, 300 to 400 milliseconds at P3, which is this association, your parietal cortex, your association cortex. That's basically it. So I can tell if I've primed Matvey to look at that water bottle, and then I show him a bunch of random stuff, and then I show him the actual water bottle, I know when he's seen it because he will have a spike at his in the P3 location, 300 milliseconds after he's seen the object. Make sense? This is cool. You could do some sort of like aim trainer with this, so you could like try and like decrease someone's reaction time. Have you guys seen those like games where they like make you shoot stuff as quick as possible? That could be like a cool idea for this. There's a lot more in-depth research. I just don't go into it. This one's like not my forte. This one's my forte though. SSVEP. So I'll let the video explain it, and then I'll go into a little bit more detail. We'll only watch like actually we'll watch all of it. It's like not that long. It's 1 minute. You guys can sit through 1 minute, right? Yeah. Oh no.
Flashing between black and white.
Can everyone hear that?
In front of them, what?
Everyone can hear it? Okay.
Imagine
Sorry?
Close the gap.
Oh yeah, sorry.
the monitor.
Sorry.
Imagine you're sitting in front of a monitor. The monitor starts flashing between black and white. When you look at this flashing stimulus, the neurons at the back of your head start dancing to the rhythm of the flash. The frequency of these neurons synchronize with the frequency of the flashing monitor. We can detect this frequency by looking at the EEG signals in the back of your head. Using the night board, we are able to differentiate between three frequencies because we coded a box in our software to turn red for 8.6 Hz, green for 10 Hz, and blue for 12 Hz. The following clip shows Gavin looking at the flashing stimuli while the box in our software changes to the appropriate color. For 8.6 Hz, we see the color. Imagine you're sitting.
Oh no, why did that happen? I was trying to pause the video. Okay, I just want to show you guys one thing.
8.6.
So if you guys look back here, this is sort of the frequency analysis, or like what's happening from the EEG signals coming from his head. You can see there's an obvious peak right here, and this peak is actually at 8.6 Hertz. It's really, really cool. So we know that his neurons and his occipital lobe are dancing or flashing at the same frequency that he's looking at. So that's how we were able to determine to like know when to change the color of the box. Oh my God. Okay.
Looking at the flashing stimuli while the box in our software changes to the appropriate color. For 8.6 Hz, we see the color we were expecting, red. And again, for 10 Hz, we see the color green, which is expected. And now the box should turn blue for 12 Hz.
Done. That's it. Any questions? Concerns? No? You guys are eager to start your project. I feel it. Okay. Alrighty. No, let's not watch that. Okay, that's it. So let's do the project walkthrough. That's basically all I had planned for the presentation. So now, should we just, I guess, like split people into two teams? Yash, what do you think? Okay, let's do that. So I think maybe split into two teams, but you guys can't be together.
Which
All of you.
What do you mean with the possible two teams working together?
Like, choose someone you haven't, like, be with someone else, not just you guys together.
Okay, hi.
Hi.
Okay, let's go. Yes. Okie dokie. Ooh, this is for you guys. Okay, you know what I'm gonna do? Since we need someone with a computer too. Thank you.
Print didn't stick to the base.
Sorry?
Your print didn't stick to the base.
Oh my goodness. Okay, this is your guys's. Okay, there might be some warping, but that's all right. It'll be fixed. Okay. So we need, okay, so Alex, are you gonna be with them? Okay, then, so you gonna be in here? Come in here. Get in here. Okay, so you four, and then you four. Okay, you'll need a computer though. You guys can't like just, it's fun to look at, not to eat, Anyways, okay, this is for you. And this is for,
I can cute with that.
okay, alrighty. And then do I give this away? Or do you guys want these? Who wants this? Actually, I have a bunch. I'll give everyone one. So, who wants the one that's completed right now? Okay, pick a number between 1 and 10.